So now we will be discussing the branch and bound method for a binary integer problem. So the branch and bound method is a way for us to efficiently solve for the values or the optimal values of a binary integer problem. In your slides, you will notice that there are several steps to solve using the branch and bound method. The first step is to transform the problem to a minimization problem. Next, transform all coefficients to a positive value. So all negative coefficients in the objective function, I have to note that this is in the objective function, should be transformed to a positive coefficient. And we will do the transformation later on. The third is to arrange the variables from lowest objective function coefficient to highest coefficient. Break ties arbitrarily. And lastly is you do the branch and bound algorithm, and you fathom a branch, or by fathoming we mean we stop extending that branch if feasible or inferior. Okay? So again, the steps is to first transform the problem into a minimization problem. Next is to transform all coefficients to a positive value in the objective function. Next is to arrange the variables from lowest objective function coefficient to highest objective function coefficient. And then we branch and bound and fathom if a branch is infeasible or inferior. And last is we do the branch and bound and fathom if a branch is feasible or inferior. We will be discussing why these steps are important after we solve the first example. Alright, this is the example given in the slides. Min z equals x1 plus 8x2 minus 3x3 plus 7x4 minus 2x5 plus 8x6, given the three constraints. First step is to transform the problem into a minimization problem. Luckily for us, the problem is already a minimization problem, so we don't have to do any transformation. But just for a quick review, if your problem is a maximization problem, this is just to transform, this is just similar to minimize negative z, if you recall from IE 41. Next is to transform all negative coefficients to positive coefficients. In this example, we have two variables that have negative coefficients, that is x3 and x5. Therefore, we have to transform their coefficients into positive. Okay, so how do we do that for a binary problem? You might think that we will just let y3, we will use y3 to denote the change, is equal to negative x3, is already a sufficient transformation. You're correct though. When we transform this, or we go x3 is equal to negative y3, when we plot that in your objective function, the coefficient of x3 will become positive. That is correct. However, it will not maintain the binary status of the problem. x3 is binary, therefore it can only have the values of 1 or 0. If we do the transformation y3 is equal to negative x3, y3 now will have a possible value of negative 1 or 0. Negative 1 is not a binary variable. Therefore, if we use this transformation, y3 becomes a non-binary variable, but we have to maintain that the problem will still have all binary variables. So in order to transform x3 into a new variable but still keep its but still keep a binary characteristic, is we use the transformation y3 is equal to 1 minus x3. In this scenario, let's try plotting it. This will also mean that x3 is equal to 1 minus y3. If we plot it in your objective function, you will get a negative 3 times 1 minus y3 and get a negative 3 plus 3y3. In this scenario, we are able to transform the objective function to a positive variable. Let's check if it still maintains by being binary. Again, x3 can only be the value of 1 or 0. If x3 is equal to 1, y3 will be equal to 1 minus 1, which will be equal to 0. If x3 is equal to 0, y3 will become 1 minus 0 or 1. Therefore, y3 is still a binary variable. So given this transformation, we are able to transform the negative coefficient to positive and keep the variables being binary. Alright, now that we've settled that transformation, we also transform x5 and say that y5 is equal to 1 minus x5 and x5 is equal to 1 minus y5. Let's substitute this to your original problem. So you will have min z equals x1 plus 8x2 minus 3 times 1 minus y3 plus 7x4 minus 2 times 1 minus y5 plus 8x6. We also do the necessary transformation in your constraints. So that's 5x1, no transformation for x1, no transformation for x2 as well. There's a transformation for x3. So minus 2 times 1 minus y3 minus 2 times 1 minus y3 plus 1 minus y3. No transformation for x4. Now aligning my variables together allows me to easily write down the new constraints given the new transformations neatly and without me missing any of the transformations. Just a little technique to help me solve the problem easier and avoid any careless mistakes. And funny enough, just as I say that, I noticed I had a misalignment in one of the variables. So this should be minus 2x5 here. Let me make it right. I did. Alright, so x5 has a transformation. That's 3 times 1 minus y5. No x5 in the second constraint. Minus 2 times 1 minus y5. So you see, I was easily able to spot the error because it didn't align. And then x6, no transformation. And your right hand sides. Okay. So to make it easier, in the next step, notice that I will, just so everything is consistent and everything is clear, I will have all the x variables transformed to y variables, just so that it's all clear. So y1 is equal to x1, y2 is equal to x2, um, y4 is equal to x4, and y6 is equal to x6. So in the next line, I will also apply this transformation. So after evaluating all of these, I will get the transformed equation y1 plus 8y2. This becomes a 3y3 plus 7y4 plus 2y5 plus 8y6 minus 5. Your constraints will be transformed as 5y1 minus y1, y1 plus y2 plus 3y2 plus 5y2. I will put all the variables first. Minus 2y, sorry, that's plus 2y3 plus 2y3 minus y3 plus 3y4 plus 3x4 minus 3y5, it's no y5, plus 2y5. This becomes plus 2y6 plus 3y6 minus y6. Then I will add in the constants. So that's minus 2 plus 3. So that's a plus 1. Minus 2 for the second constraint. And a plus 1 minus 2 on the third constraint. So that's a minus 1. It's greater than or equal to negative 4. Greater than or equal to negative 3. Greater than or equal to 2. I will just put all of constants on the right hand side. Let's do that quickly. So this becomes a plus 1, transfer there. This becomes negative 5. Greater than or equal to negative 5. Minus 2, minus 3, transfer there. Minus 3 plus 2 gives us a negative 1. Minus 1, 2. 2 plus 1, when we transpose, this gets us greater than or equal to 3. Alright? And we maintain that yi is binary. Great. The next step is now to transform or to rearrange your objective function into smallest coefficient to largest coefficient. Now, some of you may want to remove the negative 5 from the objective function coefficient. Since it's a constant, it won't be a factor in our computations. So we can drop this for now, and let's rearrange your objective function. Great. So that's min. Smallest variable is y1. So we go z prime is equal to y1. Then I like to rearrange the constraints also so that it follows the arrangement of the objective function, just so that when I do the branch and bound later, it will be a lot clearer. So that's y1 5y1 minus y1, y1. Next is y5. So plus 2y5 minus 3y5 blank plus 2y5. Next is y3. Copy your constraints. Next is y4. Oops, sorry guys, I made a mistake. Coefficient of y4 in the second constraint is only 1. I miscopied. Apologies for that. Why didn't you guys tell me earlier I made a mistake? Alright, so, oops, erased. Plus y4, that's a blank. Next is, so y2 and y6 both have the same coefficient. So as I said earlier, we break ties arbitrarily. So let's go with y2 first. And lastly, y6. And your right hand side. Great. Now from there, we can do your branch and bound method. Alright, so for the branch and bound method, I like to do it using blanks and a z value. So for the start, I will assign each variable as a blank value. 1, 2, 3, 4, 5, 6. Each blank corresponds to the values we have. This is for y1, this is for y1, y5, y3, y4, y2, y6, or basically the order that it is in your objective function. And for now, assume that if it is a blank, its value is 0 until we do not quote-unquote finalize it. And the z prime value here is equal to 0 since currently all of them has a value of 0. Now, again, what we do is we branch and bound, and we only fathom if it's inferior or if it's feasible. I will discuss that in a little while. Okay, great. So this becomes our first branch. And let us check if this branch is feasible. So if all values are 0, will it follow that, will it match all of our constraints? Or is it a feasible solution? Let's try the first constraint. 0 minus 0 plus 0 plus 0 plus 0 plus 0. Is it greater than or equal to negative 5? 0 is greater than or equal to negative 5. So it doesn't violate, or it is feasible in the first constraint. Second constraint, 0 plus 0 plus 0 plus 0 plus 0. Is it greater than or equal to negative 1? Yes, it is greater than or equal to negative 1. So it follows your second constraint as well. How about the third constraint? 0 plus 0 minus 0 plus 0 minus 0. 0, is it greater than or equal to 3? No. It is still it is, therefore, it doesn't follow constraint 3. Therefore, the first node is infeasible. So we do not fathom yet. And now we branch. When we branch, we always start with the first variable and we branch on the two possible values it can have. Therefore, the first is we branch out that y1 is equal to 0 and y1 is equal to 1. So when I say finalize, since we've already set a value for y1, we will put that in your brackets. So y1 is 0. The others we haven't finalized, so we keep blanks. 1, 2, 3, 4, 5. This is technically the same. This is technically similar to the first node. So we know that this is still infeasible. So when we can keep it as that. For the next or the right branch, so let's name this subnode 0, subnode 1. Let's name subnode 2. So we now finalize. The value is 1, blank, 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 blank. The other 5. Z prime is equal to 1 because this we get a 1 here, and then the other variables are 0. Let's now check the constraints. 5 is greater than or equal to negative 5. Yes. Is negative 1 greater than or equal to negative 1? Yes. Is 1 greater than or equal to 3? No. Therefore, that node is still infeasible. Therefore, we still cannot fathom. Since we have not fathomed or we haven't stopped any branches from growing, we continue to branch out on our nodes. We now branch out on the next variable y5, and we branch it out on both nodes. So we will have a branch wherein y5 is equal to 0 and y5 is equal to 1. Same here, a branch where y5 is equal to 0 and y5 is equal to 1. Let's try it. So this becomes 0, 0, since we've already placed a value for y5. And the rest will remain blank. Z prime is still equal to 0. About here, you have 0, 1, blank, 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 blank for the other 4. Z prime here is equal to, so y1 now has a value. Sorry, y1 is 0 to y5. So for this node, we get 0 y1 plus 2 times 1. So we get a z prime value of 2. And then let's look at your constraints. 0 minus 3 is greater than or equal to negative 5. Negative 3 is greater than or equal to negative 5. 0 is greater than or equal to negative 1. Yes. 0 plus 2 is it greater than or equal to 3? No. Therefore, this node is still infeasible, and therefore we cannot fathom. Let's name this node, sorry, just node 3, node 4, node 5. You don't necessarily have to name the nodes. This is just me naming it so that I can explain it better for you guys. Next, we assign y5 is equal to 0. So 1, 0, blank, 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 blank. Z prime is equal to 1. Notice that the left branch will always be similar to your previous node. It's because we're technically just finalizing that a blank value is 0. So we still know that node 6 is infeasible since it's similar to node 3. Next here, this is 1, 1, blank, 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 blank. Z prime is equal to 1 plus 2. Therefore, that's equal to 3. Now, let's check feasibility. 5 minus 3 is 2. Is it greater than or equal to negative 5? Yes. Negative 1 is greater than or equal to negative 1? Yes. 1 plus 2 is greater than or equal to 3? Yes. So, this node node 7 is now feasible. Therefore, we fathom, meaning we've already found a feasible solution, and that is our current value for optimal solution. So currently, we have an optimal solution, or we feasible a candidate optimal solution since we have already fathomed um, z prime. Now, once you've already fathomed because of feasibility, the next step is to look back to all your infeasible nodes and see if we can fathom because of inferiority. What do we mean by inferiority? Inferiority simply means that any other solution or any other solution after that branch will be inferior or will be suboptimal than your current fathomed solution. So we're now going to check if we're now going to check if subnodes 4, 5, and 6 will be inferior to node 7. And if we can fathom. Now, bear with me, there might be some confusion on how the fathoming for the next steps will go. Let's go to node 4. The next possible branches for node 4 is y3 getting a value. If y3 gets a value, we can automatically predict that z prime will have either a value of 0 or 3, since it's going to be 0, 0 given by these two values, and the next would be y3. The next variable to have a value is y3. If y3 gets a value of 1, z prime is equal to 3. We now check, is a z prime value of 3 infeasible to your current z prime value? Is it less? Note that we are minimizing. So by inferiority, we mean will it be less than your z prime value? 3, is it less than 3? No, it is not. So it means that the candidates it means that the branches coming out of node 4 can still be a candidate for your optimal solution or an alternative optimal solution. So we will not fathom yet. Let's now go to node 5. Current z prime value of node 5 is 2, and the next variable to get a value is y3. If y3 gets a value, your z prime value will at least be 5. Now let's check, is 5 inferior to 3? Since this is a minimization problem, we want a lesser value, or we want to maintain the lesser value. And since 5 is not equal to 3, since 5 is not less than or equal to 3, any other branch from this node will always be worse than node 7. Since any branch of it will be worse than node 7, we can stop. Why do we say again that any branch will be worse? It's because the next variables that can have values are y4, y3, y2, and y6, and all of them will just add value to 2, and it will always be greater than your current fathomed solution of z prime is equal to 3. Therefore, with that conclusion, we can now fathom this node because of inferiority. Next, let's check node 6. Possible next values for node 6 is, again, y3 to get a value. And if y3 gets a value, z prime will get a value of 1 plus 3. Z prime will get a value of 4. Again, 4 is not greater than or equal to 3. Therefore, any other node Therefore, any other branch that branches out from node 6 will be inferior to node 7. Therefore, we can also fathom it because of inferiority. Great, now we just have two branches left, or two nodes left. I know that in the slides it already fathomed node 3, but I want to check if it's a possible alternative optimal solution. So what we can do is branch out this node y3 is equal to 0, y3 is equal to 1, correct? So this becomes 0, 0, 0, blank, blank, blank. Z prime remains at 0. Still infeasible. This becomes 0, 0, 1, blank, blank, blank. Z prime is equal to 3. Now let's check. Let's name it node, sorry. Let's name this node 8 and node 9. Let's check the feasibility of node 9. Is 2 greater than or equal to negative 5? Yes. Is 2 greater than or equal to negative 1? Yes. Is negative 1 greater than or equal to 3? No, it is still infeasible. But can we fathom because of inferiority? Again, notice that z prime here is equal to 3. Next value to get is y4, meaning the next z prime value of that branch, if we continue to branch, will be equal to 3 plus 7. That's a 10, and a 10 is already inferior to your current fathom node where z prime is equal to 3. Therefore, we can fathom because of inferiority. Same goes for node 8. Node 8, the next possible value is y4 getting a value, which gets you a z prime value of 7, which is already worse than 3. So we also fathom this because of inferiority. Since we have one node left, this becomes our optimal solution. And our optimal solution is z prime is equal to 3. y1 is equal to 1. y5 is equal to 1. y3 is equal to 0. y4 is equal to 0. y2 is equal to 0. y6 is equal to 0. Now, using this and using our earlier transformations, using these values, we will get that x1 is equal to y1, therefore x1 is equal to 1. y5 was transformed, and we have x5 is equal to 1 minus y5, therefore x5 is equal to 0. The other variable that we transformed a while ago was y3. Oops, sorry. x3 is equal to 1 minus y3. Therefore, x3 is equal to... Sorry. Therefore, x3 is equal to 1. y4, y2, and y6 were not transformed. So, x4 is equal to y4, which is equal to 0. x2 is equal to y2, which is equal to 0. x6 is equal to y6, which is also equal to 0. Therefore, our final answer is x1 is equal to 1, x2 is equal to 1. Sorry. x2 is equal to 0. x3 is equal to 1. x4 is equal to 0. x5 is equal to 0. And x6 is equal to 0. Plugging this in to your original objective function, which is this. Let's just double check. x1 and x3. x1 and x3. Therefore, your optimal z value is equal to negative 2. Let's just double check the feasibility. Then x1 and x3. 5 minus 2 is greater than or equal to 4, negative 4, yes. Negative 1 minus 2 is greater than or equal to negative 3, yes. 1 plus 3, sorry, 1 plus 1 is greater than or equal to 2, yes. Great. Now, let's discuss why did we have to transform it to a minimization problem, why did it have to be positive, and why did we have to arrange. Transforming it to a minimization problem, and having all variables positive and arranging them from highest to lowest allows us to quote unquote predict that any other value will be worse than our current fathomed solution. The reason why we are able to fathom these solutions, the reason why we are able to fathom your other subnodes is because of the fact that it's a minimization problem and the nodes, and we know that we keep on adding and adding and adding the variables. We know that if we continue to branch, we will just get a worse value than our current values because we are minimizing, but we keep continue adding higher coefficients to the variables. So because of our transformation, we are able to predict the future values of the nodes, and it allows us to stop from branching out. If the transformation was not done, we would have to explicitly enumerate all of the values, all of the possible values of y1 to y6, and we are not able to confidently predict the next steps. So transforming the values allows us to fathom and to stop at our solution and cut our tree to get a feasible solution. It saves us time. It cuts us time when doing the branch and bound algorithm. Now I encourage you to try another example on your own, and please let me know if you have any other questions. Thank you.